we're going to continue with our procedures of confidence intervals and hypothesis test. And this time we're going to be talking about inference in terms of confidence intervals and hypothesis test for one mean. So just a reminder, if we're talking about the mean of the entire population, our notation here was mu. So now mu is this thing we're trying to estimate or predict in this section. So you'll notice the framework is very similar to what we've been seeing. So let me emphasize here when we're talking about confidence intervals for one mean. Again, the thing we're trying to estimate specifically is mu, that population mean. So remember, our framework for confidence interval was our point estimate. So if I'm trying to estimate the mean of the whole population, it makes sense that my point estimate, or starting point, would be the statistic x bar, the mean of the data. So that's step one. Mean of the data is used to estimate mean of the whole population. Then we had plus or minus this margin of error, because we know if we collect a different data set, we're going to get a different x bar. So we want to incorporate that in our calculations. So our margin of error has our usual two pieces, our multiplier that's going to give us the level of confidence, and our standard error that's going to take into consideration that variability of x bar from sample to sample. So when we were talking about proportions, our multiplier came from the normal distribution and it was called z star. Now we're going to call this t star. And we're going to find this in the second video, so I'm not going to go into too much detail now, but it is very similar. And then our standard error, if you remember, maybe let me write this off to this side. For our sampling distribution, we said the sample means are normal, centered at the population mean, and their variability, or standard error, was sigma over the square root of n. So here's our standard error, but we have a slight problem. We don't know what sigma is. That's the standard deviation of the whole population. So we're going to make a logical switch here and estimate that with S, the standard deviation of the data. Okay. So there's our format for the confidence interval. Same basic structure. We're just changing up the details to refer to the population mean. Now, just a reminder, we've talked about this with proportions. We're going to see the same thing here. This is very important, influences on the width of the confidence interval. So we mentioned before our confidence interval, we add our margin of error to get the upper endpoint. We subtract the margin of error to get the lower endpoint. So it's this margin of error piece that's controlling how wide our interval is. And our margin of error, we said, has two parts. This one that gives us our level of confidence. So that's my first influence, is our confidence. And we explained before, and in this case it's our T star is defining our level of confidence, that as we are more and more confident in our estimate, then the width of our interval also is going to increase because our T star increases. So more confident, you have more area in the middle, T star gets pushed out to the edges, so you get a bigger multiplier. So more confidence is a bigger T star, which gives you a wider interval, and then vice versa. And then the second part of our margin of error here that's influencing the width is our standard error. So standard error, the sample standard deviation is going to be what it is, but the sample size we have some control over. So our sample size, or n. And you'll notice that n is in the denominator, specifically as a square root, just like it was for proportions. So as n increases, our standard error is going to decrease. So sample size increases, the standard error gets smaller, which means our interval is going to be narrower or more precise. So our width is going to decrease. So same relationships we've seen before. Confidence has a direct relationship. More confident, wider interval. Less confident, narrow interval. Sample size has an inverse relationship. Bigger sample size, smaller interval. Smaller sample size, bigger interval. All right, then let's jot down our framework for the hypothesis test. So hypothesis test for one mean. We're going to have our usual steps. So first one, we need to state our hypotheses. And like you're getting comfortable with, we're going to have two of them, our null and alternative. Our research question is still going to go in HA, but since we're talking about the mean of the population, that's what our claim involves, we're going to use the notation mu. No more p in this section, it's always mu because we're talking about the mean of the population. So we have our same options. We want to make some kind of claim. The population mean is less than, greater than, or somehow just different than mu naught. So mu naught is a number from our claim. Maybe let me jot that down. Mu naught is a number from our claim, not from the data. We haven't collected any data yet. We just have some hypothesis. Population mean is related to this claim in one of these ways. And then the null, this should look really familiar. We're going to start off with our initial assumption that the population mean is in fact that value. And again, see if we can prove it's different according to our research question. Step 2, our test statistic. If you remember the general setup, I'll write it out here in the margin as a reminder. We had our point estimate. We're seeing how far our evidence or data is from the initial claim in the null hypothesis. And of course, we need to standardize this. So you'll notice we're changing letters here. Instead of Z-calc, it's going to be T-calc, and we'll explain this in the next video. But it has the same setup. So if we're talking about means, the point estimate, or my evidence, is the mean of the data. So I'm going to check out how far the mean of my data is from the null hypothesis. So the null hypothesis assumes that the mean is this number. So how far is the evidence from that initial assumption? And then we're going to standardize this, of course, by our standard error of the mean, which we saw a moment ago was s over square root of n. So there's our test statistic. Then our p-value is going to be found in much the same way. If you remember, for proportions, we use normal CDF. Here, we're going to use a function on our calculator called tCDF. I'm going to write that down just like this. I'll say with this quantity df is equal to n minus 1. I'll explain that in the next video. But just know we're going to use tCDF instead of normal CDF, and it's going to be very much the same. It's going to depend on if HA is less than, greater than, or not equal to, how we use this function tCDF. And then our last two steps are interpretation of the p-value and our conclusion. They're going to be the same as before when we were talking about 1 and 2 proportions. So I'll just write same. All right. Tune into the next video to get an idea of what this t-distribution is that I've been referencing here.